Hi, welcome to Lambda U. My name is Andy and I'm a Solutions and Support Scientist at LICOR. If you've been following all of our courses so far, you'll have learned all the steps required for preparation of Western blots and appropriate detection of the signals. In this course, we'll discuss how to properly adjust the appearance of your image so that you can conserve your data, accurately quantify your signals, and meet journal requirements for publication. We will address the different types of image manipulations and adjustments, which are acceptable and which are not, and we'll also discuss how to properly present your images to best reflect the outcomes of your experiments. Later, Jessica will provide some best practices for this step. The key thing to remember when adjusting your Western blot image is that you don't want to undo all of the hard work that you've done in preparing and imaging your blot so far. You want your images and the subsequent analysis to be reflective of that hard work, but more importantly, of your actual experimental outcomes. Some types of image manipulation can adversely affect your data, and that is something we definitely want to steer clear of. In general, image adjustments, which are typically evenly applied across the image and don't affect the quantitative signal values, are okay. Whereas image manipulations, which can sometimes be unevenly applied and will always affect your quantitative data, should be avoided. Image manipulations, whether intentional or inadvertent, can take place at multiple points throughout the acquisition and processing of your image. The first is during the acquisition itself. These kinds of manipulations are mostly down to the way that some imagers and their software work when acquiring signal information. One example is binning. This is a type of image manipulation which is actually designed into some types of imager, and is used by the acquisition software as a way to artificially increase the apparent signal from your bands. Binning works by taking all of the pixels from your original raw image and dividing them up into groups of 2x2, 3x3, or x by x squares. The signals from all of the pixels in each group are then added together to give a single value for the whole group. This can sometimes help to improve the signal-to-noise ratio, but it comes at a cost. Firstly, the overall resolution of the resulting image is going to be dramatically reduced. With 2x2 binning, this will be reduced by a factor of 4, and in the case of 3x3 binning, the resulting image resolution will be 9 times lower than it was originally. So if your imaging system has a fancy 9 megapixel camera, and it uses 3x3 binning to artificially increase the signal, you're going to end up with a 1 megapixel image. So I hope you didn't pay extra for that high megapixel count. Secondly, binning takes place after the signals have been received by the instrument. So this means that it is an artificial manipulation of the observed signal information, and the resulting images and the subsequent quantitative data are no longer truly representative of measured signal intensities. So binning should be avoided for the most accurate quantitative results. Another example of a manipulation that could take place during image acquisition is stacking. This is where, rather than taking one single image of your blot, your system actually takes multiple separate images or exposures, which are then combined together into one image. And typically, the signal intensities for each band from each separate image are added together. This should really be avoided, as presenting or quantifying a stacked image skews the differences between the different signal values, and is not truly representative of your experimental results. This is especially true with chemiluminescence, because each individual image from the stack is a different snapshot in time of a dynamic and changing reaction. Ideally, you'll choose the imager with the widest dynamic range possible, so that all the signals from your blot can be captured in a single image, without saturation and without compromising sensitivity. Let's now talk about dynamic range in more detail and what it means for your results. Simply put, the dynamic range of your hardware is the range of signals that can be captured in a single image, from the very weakest, which is the limit of detection, right the way through to the very strongest, which is the point of saturation. Any signals which are higher than this range cannot be distinguished by the detector, while those which are lower than that range may not be picked up at all. You want your system to have the highest dynamic range possible, so that you can ensure the broadest range of signals can be captured in a single image without compromising sensitivity and without saturation. If some signals on your blot are lower than the dynamic range of your detector, they will not show on the image. And if other signals are higher than that dynamic range, then they will be saturated. In that case, a band with 10 times the signal of another may appear exactly the same on the resulting image, if they are both saturated. This means that the signals from these bands cannot be accurately quantified, and also the image will give misleading visual account of your experimental results. Another factor that could affect your image and your data at the point of acquisition is the presence of imaging artifacts. Such artifacts could result from bubbles in the buffer or the substrate, uneven signal measurement and light diffraction due to a partially dried membrane, particles of dust or dirt on the imaging surface, or incomplete or uneven substrate distribution. It's important to take measures to ensure that these artifacts are avoided, as they could all interfere with the appearance of an image and the quantification of signal data. As soon as an image is acquired, it should be visually inspected for the presence of imaging artifacts, and if there are any detected, that image should be discarded and another image immediately acquired. Other image adjustments and manipulations can take place in the software after the image has been acquired. We'll take a look at these in the next lesson.